All right. We have to look at increasing and decreasing. How do you know if a function is increasing? What does it look like? So again, this is where the words you use are very important. That's what you meant, right? Oh, it's absolutely correct. But the way you phrased it was difficult. Here's how you phrase it. Remember, for a function to be increasing, we pick 2 points. So this is x1, this is y1, this is x2, and this is y2. Remember when we did slopes and everything? So we define an increasing function as this. First off, there are two ways to do this part. We can say as x goes to infinity, because we always want to go to the right. We want to go towards infinity. As x goes to infinity, what that means in this case is this, is x1 is less than x2. So if x is going to infinity, the first point has to be less than the second point. It's increasing if y1 is less than y2. Because if x1 is less than x2 and y1 is less than y2, that means an increasing function. Or another way we can say it, as x goes to infinity, y goes to infinity. How about decreasing? Same thing there. We have 2 points. Remember, we're always going to the right. X is always positive. So as x goes to infinity, in other words, what that means is x1 is less than x2. It's decreasing if y1 is greater than y2. So what this really says is as x goes to infinity, y goes to negative infinity. It's going down. Make sense? Example 1. Here's my graph. Let me draw it first. Here's my graph. Tell me where my function is increasing, decreasing, and constant. Now, this is, let's draw your picture first. Sorry. You guys waited for me. Now, when we talk about where a function is increasing or decreasing or constant, we only look at the domain, the x values. So in the first one, where is it increasing? From 3 to 5, and it's open parentheses. Why is it open parentheses? Because at 3 and at 5, the graph is not doing anything. Is it increasing there or is it decreasing there or nothing? We don't know. So that's why we always use open parentheses. Where is it decreasing?
To -1
From where to -1?
and negative infinity.
From negative infinity to -1. Where else?
5 to infinity.
So from 5 to infinity, because we're doing inequalities, we have to put a union between there. Very good, very good. The graph is decreasing from negative infinity to -1. And then it's also going from 5 to positive infinity. It's decreasing. And it's constant from where to where?
-1 to 3.
From -1 to 3. Very good. Is the graph continuous? Yeah. So we have to be able to go from negative infinity to positive infinity and not have any missing spaces. So we're going from negative infinity to -1, from -1 to 3, from 3 to 5, from 5 to infinity. So check. There aren't any holes anywhere. What's happening up here at 5, 2? What's happening at 5, 2? What's the slope at 5, 2? We know the slope. What's the slope on this side? Is it positive or negative? Yeah, it's positive because it's going up, so it's greater than 0. How about on the other side? So it's negative, it's going down. If the slope is positive to the left and negative to the right, this is a maximum. In other words, it's going up higher and then it's going down. So that means that's the highest. It's a maximum point. But since it's only this, we call it a relative maximum. Relative maximum simply means on a small domain. Is it the highest point of the entire graph? No, because it goes on to infinity and negative infinity. Does it have a minimum point? No, because all of these are constant and they're all the lowest points in this relative area. And it goes on to, so it has no relative minimum. What's the slope at the maximum point? If it's positive here and negative there, what's between positive and negative? So whenever you have a maximum, well, we call these extrema. If it's the highest or lowest point, the slope is 0 at that point. Look at another one here. Do we have extrema points here? Extrema simply means highest and or lowest. Do we have it? Yeah. Where? Let's call this point A. Is that a high or low point? So is a maximum or minimum? Minimum. We call this a relative minimum. How about this point? Point B. It's a relative maximum. How about point C? Minimum. Because it's at the bottom. I'll show you why we call these what they are.
So it's not, it can be another low point, it doesn't have to be the lowest point.
Right. All you can have a whole bunch of relative maximum minimum. There can only be one absolute maximum. The absolute maximum minimum is the highest or lowest. Do we have an absolute maximum here? No, because it goes on forever.
So infinity doesn't count.
It's not a value. You can't get to it. Do we have an absolute minimum? Because it's the lowest of all the graph. You can be a relative maximum or minima, but you can only have one absolute maxima, one absolute minima at most. So can the absolute be also relative? Yes. Because relative simply means in a small domain. So those are extremas, maxima and minima. But remember, to be a minimum, what has to happen? To the left of it, the slope is negative. To the right, the slope is positive. That's for a minimum. Just think about it. Negative goes down, positive goes up, so we have the lowest point. For a maximum, we have a positive on the left, negative on the right. So it has to go up and then down. Think of a roller coaster. The highest and lowest points of a roller coaster. You're going to the lowest part, you go down and then back up. Here's our function 0.1 x cubed minus 0.6 x squared minus 0.1 x plus 2. Here we have the graph of that function. And it goes on. We know that's the shape of it. How do we know that's the shape of the graph? Because it's a cubic function. Remember the library function? If it's an odd exponent, that means the end behavior. Both ends point opposite directions. So give me my relative max, relative min, absolute max, absolute min. So do we have a relative maximum? Where? It's at the point 0, 2. It happens when x is 0. So the relative maximum is 2 at x equals 0. Relative minimum is negative 1.604 at x equals 4.082. We want to know what the value is at what x location. Do we have an absolute maximum, absolute minimum? Does not exist. Does not exist because it goes on forever both directions. Where is it increasing? Where is it decreasing? So decreasing or increasing? It's increasing from negative infinity to 0. You only tell me the x values.
Oh, yeah.
And where else? Where else is it increasing? Yeah, it starts at this point and goes on from there. So it's unioned 4.082 to infinity. That's where it's increasing. Use your pen. It's increasing, it's going up above the pen. It stops there, starts going down, starts there, starts going back up. So these are your extrema points. It's increasing from negative infinity to 0. And then from this point to positive infinity. Where is it decreasing? It's decreasing from 0 to 4.082.
The points don't matter, like we're.
No, it's for the increasing, decreasing. All I'm looking for is the x values. Where is it increasing, decreasing? And I use those because if it's not exactly on the dot, then you use those points. So that's increasing, decreasing function. So far, so good. So in other words, we only use the x values and you never use the brackets. Now we're going to talk about a special type of function. PIE, piecewise defined function. Piecewise defined function. Just as the name entails, it's a function that's defined in pieces. Because up until now, we had that equation. That's for all x's from negative infinity to positive infinity. But here's an example. What if I want to look at this function instead? That's a piecewise defined function. How many pieces are there? 3. This is my domain. This is my range. These are my X values. This is my Y value. What is f of -5? Well, what does this represent?
X.
So here are the X's.
That one. All the signs for.
Let's see.
Neg-
Is -5, is it less than -2? Or is it between -2 and 3?
No,
-5?
less
X -5 is less than -2. So I use this equation. So I use -5 plus 1 equals -4. So the point of this graph is at -5, -4. That's my point of my graph. How about f of -3? Is it in the first, second, or third equation? Where's -3? Yeah, -3 is less than -2, so I use this equation again. So it's -3 plus 1. So the point on my graph is at that. How about f of 0? It's yeah, because 0 is between -2 and 3, so the answer is 5. So at 0, it's 5. How about f of 3? Which one? Nope.
5.
Yeah, because it's in the middle one. X is less than or equal to 3. It's 3, so the answer is 5. How about f of 4? Is it the first, second, or third? Yeah, because 10 or 4 is bigger than 3. I got to use this equation. So it's 4 squared is 16. So that's the point of my graph. And then f of 10, it's also squared. So it's 10 squared, makes it 100. So at 10, it's 100. So let's look at that function there. What this piecewise defined function. Let's look at that again and let's graph it. Notice the domain, it goes from -infinity to -2, from -2 to 3, and then 3 to positive infinity. So it's a continuous function. How many pieces are there to this function? 3. The first piece goes from negative infinity to -2. So here, up until here, I have my first graph. Then my second piece is from -2 to 3. So here's my second piece of my graph. And then for that, we take this function and draw all 3 pieces. What kind of graph is this going to look like? What kind of function is that? From our library of functions.
Linear.
Linear. So from linear equation, we need to have 2 points to draw a line. Well, we had those, -5 and -3. So we have these 2 points we can plot. So at -5, the answer is -4. I have a dot there. At -3, I have -2. And it goes all the way up to what? When x is -2, y is -1. I put an open circle there, because I cannot use -2. So when x is -2, it's -1. That's the first graph. Now from -2 to 3, I use this function. What does that graph look like?
Horizontal, ain't it?
It's a horizontal line at 5. So at -2, it's a solid dot. All the way to 3, it's a horizontal line. Was that -2, -1, 0, 1, 2, and 3? They all equal 5. And then for the third graph, from anything greater than 3, I use x squared. So you always have to start off where it says. So if I put -3 in there, if I put +3 in there, I get what? 3 squared is what? 9. So at 9, I put an open circle, because I can't use 3. Then at 4, I get 16, and we know what the graph looks like from there. It goes on, it's a curve. So there's my graph for that function. We'll look at those a little later. Let's look at another piecewise defined function. I already did that one. Let's take this one, example 6. Graph this function. 1/3 x plus 3 when x is less than 3. And then -x when x is greater than 3. Or equal to 3. One, 2, 3, 4, 6. 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4. And a couple more. So 1, 2, 6, 2, 3. So looking at this, how many pieces of the graph do we have? Yeah, the first one goes all the way up to 3 from infinity, and then goes from 3. So we have 2 parts. Always start off at the overlapping point. What do we notice about both of these equations? What are the graphs going to look like? What kind of equation is this? From the library of functions.
They're both linear.
They're both linear. So that helps us a lot. Knowing what the graph's going to look like, why does knowing they're linear going to help us? Because once we find a point, then we can use the slope to find the next point. Or we can just find 2 points and connect the dots and go forever. So the first one, let's look at this one here. At 3, if x equals 3, even though we can't use it, if we plug in 3 in here, the 3's cancel, so we have 1. 1 plus 3 is 4. So at 3, we have an open circle at 4. What would be the next logical point to use? We want an x less than 3. Well, we know the slope of this one is going to be up 1 over 3. But that's if we're going to the right. We need to go to the left. So it's easier if we use 0 because it's less than 3. If x is 0, what is our answer going to be? So there's our graph there. It's a linear equation. All we need is 2 points and we're done for that part. Now the next one. Again, start off at this point. When x is 3, what do we get here? -3. And it's a solid dot because it's equal to. When x is 4, y is -4. So the graph looks like this. There's our function. So you start off at these points, and if it's not equal to, then you put an open circle. If it's equal to, you put a closed circle. Example 7. Graph this function. Weird. Two x minus 6. Two, three, 4, 5, 6. -1, -2, -3, -4. All right, so the first equation. I look at all my x's that are equal to or less than 0. So I'll start with 0. If x is 0, what's my y value? I'm only looking at that one. When x is 0, y is 4. So I put a dot there. Is it open or closed circle? Closed because I can use 0. Less than 0, when x is -1, what is? I use a value less than 0. I use -1. What's my answer going to be?
I'm
4.
4.
It's a constant number. It's 4. No matter what values I pick, it's always going to be 4. So it's going to be a horizontal line there forever. Now, look at this next equation. For all my x's between 0 and 2, from my 0 to 2, what kind of graph is it going to look like? What does square mean? What kind of graph is squared? It's a U. Since there's a negative in front, it's going to be up and down. It's a parabola. So when x is 0, we plug 0 in there, what do we get? So that's already taken care of. When x is 1, what do we get? So we got a 3. When x is 2, when x is 2, yeah, 2 squared is 4, 4 minus 4 is 0. Is it a solid or open circle? It's a solid. So this one is a curve going down like this. The last one is a what kind of graph? Linear. So we know we need a couple of points. So start off with this one. When x is 2, what do we get? Minus 2. Open or closed? Open because I cannot use it. When x is 3, 2 times 3 is 6. 6 minus 6 is 0. So there's my graph there. There's my function. This is how you have to look at each one of them separately. Example 8. F of x is equal to x squared minus 4, x plus 2, for all x's not equal to negative 2, and 3 for all x's equal to negative 2. Draw your chart. Well, we know when x is negative 2, what does it equal? Yeah, when x is 2, negative 2, it's 3. So we have a dot there. But what do we do with this equation? We have x squared minus 4 over x plus 2. Again, they're throwing this out to you before we even taught you this thing. But if I put negative 2 in both top and bottom, it'll be 0 over 0. So what that tells us is they share that. That means something can be removed. This is a quadratic equation, meaning it can be broken up into 2 pieces. That means it has 2 solutions. It's going to be x plus 2, x minus 2, all over x plus 2. X plus 2's can cancel, so our line is going to look like this. It's going to be a linear equation of x minus 2. So what does that line look like? We have a y-intercept at negative 2, and the slope is 1 over 1, so up 1 over 1. So the graph will look like this of this one. Except I cannot use negative 2. So at negative 2, I put a hole right there. Because I got rid of the x plus twos, it's called a removable discontinuity. I have a hole there. So I have my graph, all of a sudden at -2, it jumps here, and then it goes back up to the graph. Again, I apologize for this. They shouldn't have thrown that in there because we haven't talked about that stuff yet. But that's how it works. Remember the greatest integer function? This is the last one we'll do today. The greatest integer function. Remember that from the library of functions? Which means this one means greatest integer. There is no decimals. So from 0 to 1, it's 0. From 1 to 2, it's 1. From 2 to 3, this is how the function goes. In other words, it rounds down. That's the greatest integer function. Again, it's in your library of functions. All right. That's it for that. That does it for section 2.1.